So let's discuss a few differences between the list ADT, which we covered in the first 2 weeks of the course, and the set ADT. When we talk about list specifically, we can we can have random access in the list, or we can access elements through some mechanism which is not available in the set ADT. So you cannot do something like S of I, but you can do something like L of I. This is allowed, while this is not. Okay. The other one is lists can contain duplicates, which is allowed, while in sets we cannot have duplicates. The final thing is, when we talk about the implementations, in the first 2 weeks we saw that lists are typically implemented either through an array-based mechanism or through a linked list mechanism. And when we covered lists, we described the different types of lists which you can use, which include doubly linked list, single linked list, or circular linked list, or linked list with tails and other stuff. When we discuss sets specifically, sets are either implemented in 3 different mechanisms. So one is the list-based approach, which include the array-based approach. The second one is tree-based approach, and the third one is hash tables based approach, which we are going to discuss in the next set of videos. So what I mean by these approaches is, like, let's say if we want to create a set of objects which include like these elements S1, S2, S3, what we can do is we can create this set object, or the set implementation backed up by an array. So all the operations which were associated with arrays will be carried forward in sets along with their time complexity. So let's say if I wanted to have a set, like let's call it S, if I add elements, I can just add elements to the end of the array or to the linked list. And if I want to find out if an element exists in the set S, I can do a linear search or a binary search depending on whether I'm keeping the data sorted or not. And the various time complexities of the array or linked list will be propagated when we design a set. Similarly, like if we have a tree-based set, what we can do is we can define like a BST, and let's say if I have an item S1, it will be the root, which is the set is empty. Now S2 is greater than S1, so it will be on the right, and then S3 is greater than S2, so it will be on the right of S2. You can also use like balanced trees to again get better performance. So all the complexities for the balanced trees and trees which we saw, which is like, let's say if insertion, deletion, or search in a balanced tree was of the order of log n, and if we are using a balanced tree data structure to back up our sets, then all the common operations, which is addition, removal, and search, will be of the order of log n. While if we use an unbalanced tree like a BST, then it will be of the order of O of n in the worst case. Now if we use hash tables, you're going to see that this time complexity, if it is a hash table based set, is of the order of O of 1, which is our desired outcome, which is can we do actually faster than even O of log n search. So this is the asymptotic complexity. Technically it's O of 1 plus k, where k is the complexity of the hashing function, but we are going to discuss all this terminology in the next set of videos when we cover hash tables. Now let's discuss a little bit about sets in C++ specifically. Sets in C++ are implemented in 2 different versions, which is one is called the ordered set or the regular set in C++, and the second one is unordered set. Set in the STL, like this set, which is the ordered set, is backed up by a tree, while unordered set is backed up by a hash table. So when we talk about the tree-based set, most operations will be of the order of log n, while most operations for hash table will be of the order of O of 1. So you might be wondering why even be bothered about this set, the ordered set version rather than the unordered set version. So again, there are trade-offs. In some problems this might make more sense, while in another problem this might make more sense. And why that's the case is because although the time complexity is faster, hash tables might take more space when compared to sets. Okay, and you're going to see that once we cover like hash tables. So let's discuss the differences. The set or the ordered set actually keeps a track of the elements in the ordered set are sorted, which is if we have a balanced tree or a balanced BST, you can just do an in-order traversal of that tree and get all the order of the elements, while in an unordered set, they are not ordered, which is like if I print an unordered set, it will just display random values rather than in a sorted manner. How we initialize sets in C++, if you have the ordered set or the regular set, you just do a set followed with the type, and then you pass the template argument for the type and just name the set like I'm naming it S. While an unordered set is represented as unordered underscore set and then followed with the template parameter. Some of the common methods, you can actually read the entire interface at this link, but some of the common methods that are allowed by the set C++ STL is insert, erase, find, count, size, and empty. So I'll go through each of them one by one. Insert inserts an element, erase erases an element in the set, find searches an element, count returns the count of the element. So the count can only be 0 and 1 because sets do not contain duplicates. Size returns the size of the set, which is how many elements are in their set, and empty returns whether the set is empty or not. Now this is for an ordered set, but for an unordered set, you, in addition to all these functions, you also have some other functions that include bucket size, load factor, and so on. What they mean is bucket size is the total size of the bucket. Like once we go into hash tables, you will understand more about this. And load factor means, like, let's say if we have some space in our table, how many space, what is the ratio of the number of occupancies versus those that are empty. So it gives you kind of a number, and we are going to discuss the significance of load factor when we start hash tables. Now the typical implementation, so set in C++ is backed up by binary search trees, and if you see the original version, I think the current implementation has red black trees which implement the set ordered set in C++. In Java it's also called the tree set version, and unordered sets are backed up by a hash table, or it's also called a hash set in Java. Time complexity, again O log n for a self-balancing tree, so it's backed up by a red black tree, so that's why most operations, these ones, will be of the order of O of log n. For the unordered set, since they are backed up by a hash table, most operations will be of the order of O1 plus O of k, and depending on your hashing function, which again we are going to describe in the next set of videos, the typical complexity will be O of 1 plus O of k. So let's discuss a quick example of sets in C++, and then I'm going to end this video for sets. You can find the entire code at this link. So here I have defined an ordered set, which is like set S1 containing integers. Now what I'm going to do is I'm inserting these numbers, which is I insert 5, then I insert 2, then 4, then 11, and then 2. So since 2 is already there, it will do nothing. Next, if I want to iterate over the set, I cannot do something like S of I. So I need to create an iterator. Like either you can do something like this, which is you have a for loop that has an auto keyword. You can use the auto keyword, and let's say your variable is X and your set is S1. So you can do something like this and just do cout X. So that should print the entire set. Or you can define explicitly an iterator, which is this is how you define an iterator to a set, which is set of integers. It's an iterator to the set of integers. And next, when we print these, so you start from s1.begin and you make sure you do not traverse the entire set, so you end at s1.end. If you print this, you can see, like, although we added numbers in some random order, the actual result is ordered, which is you can see these numbers are sorted, which means internally they are represented as a sorted set, or behind the scenes, since it's tree based, it's already sorted. For an unordered set, which is a hash based set, let's say if I add the same numbers to the set, which is our set looks like 5, 2, 4, and 11, 2 happens when we insert 2, nothing happens. Then I create an iterator to the unordered set, and if I print this, you can see the numbers are being printed in random order. Like it's not even being printed in the same order in which we were inserting. So it's completely random. Once you understand hash tables, you'll see why it's random, because it really depends on the hashing function. Some other methods that are available just to unordered set, which includes bucket counts. So it shows you what is the size of the bucket, which means let's say if we had 4 elements in this, our hash table, which has like, you can think of this as it has 7 different rows, okay, one after another. And load factor is nothing but what is the total occupancy in this table. So we have 4 elements in this table divided by the bucket count. If we do that, you'll see that this number is nothing but 4 divided by 7. So I can write this here. And max load factor determines again a particular value, which is what can be the maximum maximum load factor. And once we discuss the significance of this term, you'll understand this more. But that is the general idea of the sets. These are a really important data structure because they allow you to search really fast in a set of objects, and they kind of like back a lot of other data structures. So they are technically the most fundamental data structures are sets and maps or tables. So in the next set of videos, we are going to start with our map data structure. Thank you.